Hello class. Today in this video we are going to talk about how the kinetic molecular theory explains physical changes and properties. So some physical changes and properties that we'll be talking about will be dissolving a solid in a liquid, thermal expansion, as well as diffusion. Now don't forget to take notes, so take out your lecture note package. It should be chemistry topic 2.3. Okay? All right, so let's move on to the first one. Using connected molecular theory to explain dissolving a solid in a liquid. So first of all, dissolving, the definition for that is a solid completely mixes with the liquid to form a solution. So particles in a solid are in constant random motion due to their kinetic energy. And so are particles in a liquid or a gas. Okay, so if you take a look at the pictures on the right hand side here, as you can see, we have the solid particles in gray, and then the blue particles, they are liquid particles. Okay, so as we know from previously, particles in a solid, they vibrate, right? And then particles in the liquid, they slide and pass to each other. So what happens is when you dissolve a solid, for example, sugar, into a liquid, water, for example, you will have, because all these particles are in constant motion, the particles in sugar, they move randomly and constantly into the empty areas between the liquid particles. And we know that there are empty areas between the liquid particles because, these particles in liquid, they have a little bit more energy, right? They slide and pass to each other, and there's more space between them. So as you can see here, sometimes occasionally you will have the solid particles moving into the space between the liquid particles, and eventually you will have basically the solid particles more or less evenly distributed in between the liquid particles, which are in blue. So you will have basically a sugar solution. The sugar is now dissolved. So a question right now on the screen for you is, what do you think will happen? And why would sugar actually dissolve faster in hot water? So I'll let you think about that. So pause this video and think about that, and I'll explain a little bit. Okay, so hopefully you have some ideas in your head. So essentially, the reason why sugar dissolves faster in hot water is because, again, when you increase the temperature, you are essentially supplying these particles, these liquid blue particles, more energy, right? There will be a little bit more space, and the movement will be a little bit more dramatic for the liquid particles. And then there will be more space between the liquid particles, correct? And because of that, now, because there's more space between the liquid particles, these solid particles in gray, they're more likely to get into these empty spaces between the blue liquid particles. And this is why eventually you will take a little bit less time to reach a more or less distributed gray solid particles in between these liquid blue particles. Okay, so that is why sugar dissolves faster in hot water. All right, so that is KMT and how KMT can be used to explain dissolving a solid in liquid. And now let's take a look at thermal expansion. What does that mean? Well, first of all, we know that solids, liquids, and gases, again, they're all made out of particles. These matter, they're all made out of particles. And as you increase the temperature, or as you increase the amount of energy you give to these particles, they will move around more, which means the volume will expand a little bit more, okay? And when you remove the energy by decreasing the temperature, the particles, they will, again, they will be more quiet, right? Because now they don't have as much energy, and their attraction between them is pretty big. So they would tend to contract when it's cooled. So what does the word thermal expansion really mean? So let me just break this word, a compound word, into two separate words. So as you can see, thermal, basically it means heat or anything related to heat. Expansion means something that can expand, right? For example. So thermal expansion, the definition for that is just the expansion of heated materials. So heating, we know that it will increase kinetic energy of particles. It will cause the particles to vibrate faster and move slightly apart. This is an example for particles in a solid, okay? And as a result, material as a whole, they will expand. And from the review, we know that, right? Generally speaking, if you move from solid liquid to gas, essentially you'll have an increase in the amount of space between the particles, which means there will be a higher volume going from solid, liquid, and gas. All right. So why is thermal expansion important? So expansion joints, they are incorporated when building bridges to prevent damage by allowing material to expand and contract with changes in temperature. Okay, so when a solid is heated, we know that its particles will gain more energy and they will vibrate faster. And then they will move a little bit further apart, and the solid again will expand as a result. So I'd like you to think about why that is important when building a bridge. Why do we need that kind of flexibility there? For example, in BC and also in Ontario. And do you think it will be more problematic if we don't have any expansion joints in Ontario compared to in BC? So think about that. And so now let's move on to the next slide, which is using KMT to explain diffusion. So what is diffusion? Well, diffusion is the movement of one material through another. And diffusion is particles, again, moving from an area of high particles concentration, with that being said, just lots of these particles, to an area of low particles concentration. Okay? So just to give you an example here, have you ever wondered why the smell of toasted bread travel through a room to your nose? Well, because of diffusion. So odors come from gases that have specific smells, okay? So again, when you toast the bread, essentially what you're trying to do here is you are applying energy, you're giving energy to these particles, okay? And again, the particles in the kitchen, now they have a lot of these gas particles. They are in high concentration. There are a lot of them in the kitchen. And because of that, again, definition for diffusion is the particles would travel from an area of high particles concentration to an area of low particles concentration. And because there are not a lot of particles somewhere around your nose, as the time went by, you will smell it, because this is how particles move. They tend to move from where there's a lot of them to an area where there's not a lot of them. All right, so diffusion is actually everywhere. It occurs inside our cells as well. So for example, gas exchange. So let me explain that. So as you know, we breathe in oxygen and we breathe out carbon dioxide. Well, how does that work at a cellular level? Well, this is how it works. The lung cells, they will have oxygen because we breathe those in. So the oxygen would be diffused into, we move down the concentration gradient. Again, it will move from an area of high oxygen particles concentration to an area of low oxygen particles concentration, right? So inside the lung cells, there are a lot of oxygen. And inside our red blood cells, which are basically carrier for gases, they have a really low oxygen concentration. So what happened is the oxygen would diffuse down through the membrane into the red blood cells. And then in red blood cells, there are really high concentration of carbon dioxide because, again, red blood cells, they're carriers in our blood. They literally just like FedEx drivers and delivery person. They take up these carbon dioxide from other parts of our body, from other body cells, for example, muscle cells, and then they transport it to somewhere around the lungs, and then they will basically deposit or take off the carbon dioxide to the lung cells, and they would take up again the oxygen. And now with the oxygen gas inside the red blood cells, they would travel towards the rest of the body to supply oxygen to the other cells so that they can do cellular respiration, right? So this is just some extra information for you, just to prove that diffusion is everywhere and occurs inside us too. So to further explain this concept, diffusion, I'm going to show you a simulation. All right, so this is a simulation. Let me just quickly guide you through what you're looking at here. So on the screen here, I have a box. This box, it's divided by a green divider, okay? So on the left-hand side, I have 30 of the blue particles. And on the right-hand side, I have 30 of these red particles. And as you can see, there are 0 of the blue particles on the right-hand side of the box, and there are 0 red particles on the left-hand side of the box. So what I want you to do now is I would like you to predict what would happen if I remove the green divider. So pause this video and make some prediction. All right, so I'm gonna remove the divider now and pay attention to what happened. So what do you see here? Well, what you see is that you will have the blue particles started to move from an area of high blue particles concentrations, area where there's a lot of them, for example, left-hand side, to an area where there were not a lot of them, or 0 with them. So as you can see, the blue particles will start to move towards the right-hand side, and then the red particles will start to move towards the left-hand side as soon as I remove the divider. And eventually, what do you see? Do you see, again, one area with higher concentration of blue particles? Or do you see one area of higher concentration of the red particles? Well, the answer is no. Right now, more or less on both sides of the box, you will have kind of the equal amounts of blue particles and equal amounts of red particles. And this is what we call eventually will reach equilibrium. But why would that happen? Well, again, as you can see, these particles, they never stop moving. They're constantly moving. Again, this is one of the key concepts of the kinetic molecular theory. Particles of matter, they're constantly in motion, and they're in constant motion, right? So as you can see, eventually, again, the particles will move from an area of high concentration to an area of low concentration, and eventually we'll reach something called the equilibrium. So that is it for this class. Don't forget to answer these following questions also on your notes too. They're also written on your notes. So the first question is, can you use KMT to explain why a balloon in a hot car will expand and may eventually pop? And also explain why does sugar dissolve faster in hot water? And also please explain what might happen if a bridge were built in BC without an expansion joint. So explain that. So don't forget to fill out your note and answer these questions. Although they would not be graded, I will be checking them in class tomorrow or next week to see if you have completed them, okay? And just a little summary of what you just learned. Again, the kinetic molecular theory, they can be used to explain physical changes and properties such as dissolving sugar, for example, in water, thermal expansion, as well as diffusion. All right, so we'll see you all in class.